Let's practice finding the GCF of two given numbers together. And to do so, we're going to practice using two different strategies. One is going to be using prime factorizations, and the other is going to be using the ladder or the cake method. Now, for most of these examples, I'm going to go ahead and make the prime factorizations in my head or out loud in this video, but feel free to pause the video at any time and draw out the prime factorization trees so that you can go ahead and get them as well. So for number one, we have 12 and 8, and I'm going to start by just writing 12. And I know I can divide it by 2, that would be left with 6, and then 6 breaks into 2 and 3. So this would be the prime factorization for 12. Now for the 8 I know I can divide by 2, so I'm going to put a 2 here. We'd be left with 4, and then 4 would break into 2 times 2. So these are the prime factorizations for 12 and 8. Once you have their prime factorizations, you're just going to go ahead and see which ones they have in common. So it's clear here that they both have a 2 and they both have another 2. Now, once we've identified their common prime numbers, all we have to do is multiply them together. So 2 times 2, and that's going to equal 4. And that's going to be the GCF, or the greatest common factor, between 12 and 8. And so while that was using prime factorization method, here is going to be the ladder or the cake method, whatever you want to call it. We just stack the two numbers next to each other like this, and you think of any number that goes into both of them. If you think of 4 right off the bat, that's great. 4 times 3 is going to be 12, and 4 times 2 is going to equal 8. And once you realize that 3 and 2 have nothing in common, then this 4 is going to be that GCF, or the greatest common factor, right? This thing right on the side here, that's going to be the GCF. All right, so 4 is the greatest common factor. This 3 and 2 at the very bottom here, we call them relatively prime. So this 3 and 2 have nothing in common. Their GCF would be 1, so you know you can stop. Alrighty, for number 2, we have 15 and 9. So I'm going to go ahead and write this 15. For the prime factorization, I think we can divide by 3, which is a prime number, and it would be 3 times 5. And then for 9, 9's a pretty short one too. It just breaks into 3 times 3. So very short prime factorizations. Now, what do they have in common? It looks like they just have the 3 in common here. So if that only has one thing in common between the two, it's just that 3, then 3 would be the greatest common factor between 15 and 9. Okay. Now, if we're going to go ahead and write these side by side, this 15 and 9, we can use the ladder method and see what do they have in common. If you can think of this 3, then that hopefully makes sense because that's what we just got using the prime factorization method. 3 times 5 is 15, and 3 times 3 is equal to 9. This 5 and 3 at the bottom are relatively prime. Their GCF is 1, so we can stop there. And this 3 over here that we just have on the side, this is going to be the GCF. Okay, let's move on to number 3. For number 3, we have 24 and 18. So for 24, I think we already did this one, so you can copy that prime factorization if you want. But we know 2 times 12, 12 breaks into 2 times 6, and 6 breaks into 2 times 3. So that's the same prime factorization for 24 we got earlier. 18 can divide by 2, and we're left with 9, and 9 breaks into a 3 times 3. All right, so what do they have in common? Well, they both have a 2, and they both have a 3. All right, so I think that's it between the two. So the GCF is going to be equal to 2 times 3, and that is going to be 6. 6 is the greatest common factor for 24 and 18. Now, if you want to use the ladder method, let's go ahead and double check this, 24 and 18. Maybe you can start with a 2 if you're not sure. 2 times 12 would be 24, 2 times 9 would be 18, and 12 and 9, I think they still have something in common. Let's go with a 3 here, right? So 3 times 4 would get you 12, and 3 times 3 would get you 9. And now at this point, this 4 and 3 are relatively prime. They have nothing in common besides 1. And so this 2 and 3 on the side here, if you multiply them together, 2 times 3, that's going to equal 6. So that would be the GCF, but we already knew that. It just confirms that this is true. Okay. Moving on to number 4, we have 40 and 30. So 40, let's see, it can break into 2 times 20. 20 can break into 2 times 10. 10 can break into 2 times 5. So that's the prime factorization for 40. And for 30, let's see, we have 2 times 15, and 15 breaks into 3 times 5. So these would be the prime factorizations. They have a 2 in common, and they also have a 5 in common. So if we go ahead and multiply those common prime factors, if we multiply 2 times 5, that's going to equal 10, which is the GCF for 40 and 30. Okay. Now over on the side, let's try this using the other method here. So let's stack them next to each other. If they both end in 0, we should be able to divide them both by 10. And dividing both by 10, we're going to get 4 and 3. And 4 and 3 are next to each other, so they're definitely not going to have anything common besides 1. And so this 10 on the side here That's going to be the GCF. And that checks out because that's what we got earlier. For number 5, let's see. We have 30 and 18. So 30, we just did this one, right? So that's 2 times 3 times 5. Again, feel free to pause if you need to make trees. For 18, we actually did this one in number 3. So that's going to be 2 times 3 times 3. When you've done enough prime factorizations, you'll start to memorize some of these as well, just from doing them so much. They both have a 2 in common and a 3 in common. So the GCF is going to be multiplying whichever ones they have in common. So 2 times 3 here, that's going to be 6. So 6 is the biggest number that goes into 30 and 18 evenly. All right, if we write this 30 and our 18 on the side, looks like, I don't know, I think most people would maybe come up with 3 as their first number. 3 times 10 is 30 and 3 times 6 is 18. Now 10 and 6 are both divisible by 2. So if you put a 2 on the outside here, 2 times 5 is going to be 10, and 2 times 3 is going to equal 6. Now 5 and 3 are both prime. They have nothing in common, so if you multiply the 3 and 2 on the side together, 3 times 2, that'll equal 6, which is also the GCF. Okay, so that checks out. For number 6, we have 36 and 27. These are new numbers. 36 breaks into 6 times 6, but each 6 breaks into 2 times 3. So we're going to end up with 2 2s and 2 3s. And for 27, that's 3 times 9, and 9 breaks into 3 times 3. So these would be the prime factorizations. It seems like they both have a 3 and another 3, and I think that's it, right? So the GCF here will just be the product of 3 times 3, which is equal to 9. That would be the GCF. Okay. If we go ahead and use the other method, 36, 27, if you know your 9 times tables, you could probably just think of 9 right away in the beginning here. 9 times 4 is 36, and 9 times 3 is 27. 4 and 3 are neighbor numbers, so they never have anything in common. And so we can't go any further because they're relatively prime. Their GCF is 1. And so this 9 here is the GCF, and that checks out with the prime factorization method. For number 7, we have 60 and 48. For 60, I'm thinking we can definitely divide by 2. That would be 30. 30 can divide by 2. That's 15. 15 breaks into 3 times 5. And then for 48, let's see, we can definitely divide by 2. That's 24. And we did earlier 24 a few times. 24 is just 3 2s and a 3. So 48 should just have one extra 2 on there. Okay, so they both have a 2. They both have another 2. And it looks like they both have a 3. Okay, so this time they have 3 common primes, so the GCF is going to be the product of 2 times 2 times 3. 2 times 2 is 4, 4 times 3 is 12, so 12 is going to be the greatest common factor that goes into 60 and 48. Now using the other method, this one should be a little faster in general. So if you know your multiplication facts, you might be able to come up with 6 right from the beginning. You might think 6 times 10 is 60, and then 6 times 8 is 48. Then you look at 10 and 8 and realize they're both even numbers. You can divide them both by 2. So they'll get 5 here and 4. And these are neighbor numbers, so they can't go any smaller. They're relatively prime, or their GCF is 1. And so if you multiply 6 times 2 on the side here, 6 times 2 is 12. 12 is going to be our GCF. All right, cool. For number 8, we have 56 and 42. So for 56, let's see, we have maybe 7 times 8, but 8 we know is 2, 2, and 2. And then 7 is prime. And for 42, 42 is what, 6 times 7, but 6 breaks into 2 times 3, and 7 is prime. All right, so what do they have in common? They both have a 2, and they both have a 7. I think that's it. So the GCF here will just be the product of 2 and 7, which is 14. That would be the GCF. Using our other method, we have 56 and 42. Let's see what they both have in common. I think maybe 7 would be a pretty common number people would think of. So 7 times 8 would be 56, and 7 times 6 is 42. Now 6 and 8 are both even, so maybe we would think of 2 here. 2 times 4 is going to be 8, and then 2 times 3 would equal 6. 4 and 3 are neighbor numbers again, so they are relatively prime. Their GCF is 1. 7 times 2 on the side, that's going to equal the GCF of 14. All right, cool. Let's move on to number 9. For number 9, we have 33 and 55. So for 33, that's equal to what? 3 times 11. they're both prime numbers, so you can stop. And then for 55, that's 5 times 11, so those are both prime numbers, so we can stop as well. Now it seems like these both have this 11 in common, and I think that's it. So this one's a pretty quick one. The GCF, or the greatest common factor, is just going to be 11. Using the ladder method, or the cake method, a little upside down cake, building downwards, seems like 11 would be their GCF right from the beginning, and then that's the only thing they're both divisible by, so we're left with 3 and 5, which have nothing in common. They're both prime numbers, and so this 11 on the side here makes sense that it is our GCF. Okay, moving on to number 10. Number 10 looks like we have 24 and 35. So 24 we've actually done a few times here. If you remember it great, it's 2, 2, 2, which makes 8, and then 3. And 35, I think, is just 5 times 7. Pretty short. Now notice they have nothing in common here, and so if you ever notice they don't have anything in common, please don't say that there's no GCF, just say that the GCF is equal to 1. Okay, so even though they don't have anything in common, keep in mind that you could technically multiply both of these by 1, and that's what they would both have in common here, this 1 and this 1. All right, so two numbers will always have a GCF. If you can't find it, just say it's 1. What this looks like using the ladder method is you stack these next to each other, 24 and 35. You think for a little bit, try to divide them. Can't think of anything. If you're absolutely sure, put a 1 on the side and keep the 24 and 35. If you were careful, that means that these have nothing in common, and then the GCF here is going to be 1, which is what we got here. If you look at the prime factorization, it should confirm that they have nothing in common. For number 11, we have 72 and 54. So for 72, let's see, that's 8 times 9, but we know 8 breaks into 2, 2, 2, and 9 breaks into 3 and 3. And for 54, 54 breaks into what, 6 times 9, but 6 breaks into 2 times 3, and 9 breaks into 3 times 3. So that should be the prime factorization. They both have a 2, they both have a 3, and it looks like they both have another 3. So the GCF is going to be the product of all those. So it's going to be 2 times 3 times 3. 2 times 3 is 6, 6 times 3 is 18. So 18 is the greatest common factor here. Let's see if this checks out using our other method of 72 and 54. I think maybe a multiplication fact you might think of is probably 9. 9 times 8 is 72, and 9 times 6 is 54. And for this 8 and 6, they're both even numbers. You can divide them both by 2. 8 divided by 2 is 4, and 6 divided by 2 is 3. 4 and 3 are neighbor numbers. They have nothing in common, so they're relatively prime. 9 times 2 on the side here are going to get the GCF of 18. That's the GCF. All right, moving on to number 12. For number 12, we have 13 and 39. So for 13, what's the prime factorization for 13? It's just 13, right? It's a prime number. And for 39, that's divisible by 3. It happens to be 3 times 13. All right, so in this case, it looks like this 13 and 13 are the only thing they have in common. So the greatest common factor for these two numbers is just going to be 13. All right, 13 fits into 13 once. 13 fits into 39 3 times. So if we go ahead and take these two numbers and stack them next to each other, we know hopefully that 13 goes into both of them. 13 goes into 13 one time, and 13 goes into 39 3 times. Now 1 and 3 have nothing in common besides 1, so they're relatively prime, where the GCF is 1. And so the GCF of 13 and 39 is going to be 13. Moving on to number 13. For 13, we have 80 and 48. So for 80, let's see here. I know that's going to be 8 times 10. And then let's see, 8 breaks into 2, 2, and 2, 2, 2, and 2, and 10 breaks into 2 and 5. Now for 48, that's 6 times 8. Now the 6 will break into 2 times 3, but the 8 will break into 3 2s. So 1, 2, 3, and another 3. Okay, so they both have a bunch of 2s here, it looks like. Again, if you need to pause and just make the tree, go ahead and do so and see if you can get the same prime factorization. It looks like they have a bunch of 2s in common. So the GCF is going to be the product of all of these. So it's going to be 2 times 2 times 2 times 2. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So that's the greatest common factor. Now, if we're going ahead and using this other method, using 80 and 48, right from the start, I'm thinking We could go with an 8 here, so 8 times 10 would be 80, and then 8 times 6 would be 48. And for 10 and 6, they're both even numbers, so we can use a 2. 2 times 5 is 10, and 2 times 3 is 6. Now 5 and 3 have nothing in common, so we just have an 8 and 2 on the side. 8 times 2 is 16, so that would be the GCF if you multiply those two together. Alrighty, so for 14, we have 51 and 34. So for 51, you might think it's prime, but if you add 5 plus 1, that is 6, which means it's divisible by 3. So this is actually 3 times 17. And for 34, that's an even number, so we can divide it by 2. It happens to be 2 times 17. Alright, so it looks like they have just a 17 in common, so we can say the GCF, or the greatest common factor, is 17. 17 fits into 51 3 times and fits into 34 2 times. Go ahead and put 51 and 34 next to each other. We know that 17 is what they both have in common. 17 times 3 is 51, and 17 times 2 is 34. So this 3 and 2 down here are neighbor numbers, so they are relatively prime, or their GCF is 1. So the GCF for 51 and 34 is going to be 17. That's the GCF. For number 15, we have 120 and 72. So for the number 120, this is a pretty big number here. I know we can divide by 2, that's 60. We can divide by 2 again, that's 30. We can divide by 2, that's 15. And so 15 breaks into 3 times 5. All right. Now for 72, 72 is what, 8 times 9? 8 is 2, 2, 2, and 9 is just 3 and 3. Again, if you need to pause to make a tree, go for it. They have a 2 in common, 2 in common, 2 in common, and a 3 in common. So let's see what the GCF is going to be. The GCF is going to be 2 times 2 times 2 times 3. 2 times 2 is 4, 4 times 2 is 8, 8 times 3 is 24. So it seems like 24 is the GCF for 120 and 72. So let's see, 120, 72. What would you do if you didn't know the answer already? I don't know, maybe you might choose a 6 first, possibly, because you might know 6 times 2 is 12, so 6 times 20 would be 120. Then you might know 6 times 12 is 72. If you didn't, you could have used a smaller number like 2 maybe to start, or 3. Now for 20 and 12, I might think of 4. 4 times 5 is 20, and 4 times 3 is 12. And this 5 and 3 have nothing in common, so if you multiply the 6 and 4 on the side, you should get the GCF, which you do, which is 24. All right, cool. Last problem here, number 16, we have 133 and 285. Now let's see here. 133 kind of looks like a prime number. I can't think of what it might be divisible by. I'm going through the rules in my head. Maybe we can try 7 because it looks kind of weird. If you double the last 3, that's 6. 13 minus 6 is 7, which is a multiple of 7. Okay, so we know we can divide this by 7. I think it's going to be 7 times 19, if I'm not mistaken. 7 times 20 would be 140, and it's 1 less 7, so that makes sense. Now for 285, let's see here. It is divisible by 3, right? Because 2 plus 8 plus 5 is 15, which is a multiple of 3. So we have a 3 here. I think that would be, let's see, we'd be left with 95, I think, right? And so 95 can divide by 5, so it'll be 5 times 19. So let's try to think about this real quick. 5 times 19 is 95. 95 times 3, that is 285, okay? So these should be the correct prime factorizations if we did them correctly. And it looks like they have these common prime factors of 19, and I think that's it. So the GCF between 133 and 285 is 19. And if we want to go ahead and use the other method here, it's definitely less writing, 133 and 285, but you got to be able to do some more division maybe in your head. And so 19 goes into both of these. Turns out 19 goes into 133 7 times. The prime factorization kind of helps with that. And then 19 times 15 is 285, just because 3 times 5 is 15. This 7 and 5 have nothing in common anymore. So this 19 over here on the side is indeed the GCF. So there you have 16 different practice problems on finding the GCF, or the greatest common factor, for two given numbers. And we use two strategies. One is using the prime factorizations, and we just multiply the common primes. And the other one was using the ladder method, where you can pull out anything you see that they have in common, and you can go to bigger numbers first if you would like, and it can save you some time. So I hope you found this video helpful. As always, keep up the great work, and I'll see you in the next one.